Hi all, welcome back to another class. So in today's class, we'll be discussing about CT. So in under CT, the basic principle of CT and the hardware, like all the CT basic principle generation and the instrumentation. So we'll be discussing about that. So I'll share my screen. So starting with the CT introduction, we learn about basic principle and generation. So in this today's class, we'll discuss about the history, basic concepts like main concepts on the CT and the principle, CT generation. So going to the history, in the year of 1895, William Conrad Röntgen discovered X-ray, followed by 1917, J. Radon have developed the reconstruction technique. So he have proved that an object we can reconstruct it into 3D by different projection. And in the 1940, Frank and Takahashi have published the principle of axial CT. That is on the year of 1940. And in the year of 1963, Alan Komark formulated that X-ray absorption in tissue and the development theory. And later on in the year of 1972, so Godfrey and Hounsfield, they have announced and they demonstrated first computer tomography machine, which is called as CAT scan. So CAT stands for computed axial tomography scan. So that time, the scanner was known as EMI scanner, which was a prototype, and it was in the hospital at Kings and Morley Hospital. And US have installed this in the year of 1973, and year by 1980, like around 3 million CT scans have been started recorded. So first scan which have been done for a brain tumor patient, and the first doctor who have used this is Dr. James Ambrose in the year of October 1971. So going to the basic principle, I hope you all know there will be an X-ray tube, beam filter will be there, which will filter off the beam, and there will be collimator, and from the collimator, X-ray will reach the patient, and through the patient, X-ray will be absorbed and it reaches the detector, and from the detector, it will be sent to the computer. So main definition for the basic principle is that multiple projections of an object can be reconstructed into several reconstructed of this internal structure of the object. So we can with the help of multiple projection we can reconstruct the internal structure of the objects can be reconstructed. So the CT image show you the radiographic tissue, organs, bones and all, and it give you good resolution, and we can get the 3D image also. So we have field of view. The field of view is an area coverage is made of slices, voxels, and pixels. And the pixels are given an algorithm value. Like each pixel will have an algorithm value. So this is your matrix. So this entire thing is your matrix, and each column here inside is the pixel. And if when we take it in a 3D form, see this is the, and only this if it's in a 2D we call it as pixel. When it is in the 3D form, we call it as voxel, volume. So in each pixel, there will be each value will be there. Numerical data will be there for each pixel, which represents the image, and we reconstructed it into the image. Okay, so this is the basic principle theory. So here, consider this part as an object, and we have cut the center boxes. Center part have been cut in the shape of plus. And what happened? We have like X-ray will be passed through this way and this way, and X-ray absorption or the linear attenuation coefficient for each row will be each horizontal and vertical ray will be calculated. So here it's 1, 2, 3, 4, 5. Here 4, 2, 4, 5. Say that is horizontal sum ray, and this is the vertical sum ray. This is in the 2D. And now what we'll do? We make it into a this is 3D. We making it into a 2D thing. So this pixel, will find out this pixel value by summing the horizontal sum and vertical sum. So here it will be 5 plus 5. So here it will be 5 plus 4. Like that we'll be summing. Here it will be 5 plus 2. And here it is 4 plus 2. Like that all column will be summed, and we get a value like this 10, 9, 7, 9, 10. Like that we get the each pixel a value. And now what we do, each number will give the shades of gray in the order, or like in the, like from 10 to here, which is the highest one is the 10, the lowest one is 4. So the highest one they'll give shade of white, and the lowest one will get the shade of black. So like that we'll arrange different shades of gray will be there. So the area where 10 is there, it will be white color. 9 little bit darker to the white, like that. 4 coming to the 4, it will be black. So you'll get an image like this. And later on this image will reconstruct it into two way in the sense, this is the two-way. In the first image, the number which is more than 10 and less than 10, like that will the shades of gray will divide into 10, like that. The number which is 10 or more than that will give a white shade, and the number which is 10 less than 10 will give black shade. So whatever number is less than 10, everything will be given dark shade, and whatever is above 10, like here we have 10, will be in the white shade. Another kind of reconstruction is given here, number above 6. So here these all part, like here you can see this 6, like this 6 6 6 6 6 4. Other than this, number above 8 will give, sorry, above 6 will give white shade, and 6 and below 6 will give black shade. Like this you get the reconstruction. So similarly we reconstruct the image. So each value will have each linear attenuation coefficient, which will be given the different shades of gray. So CT number, going to CT number is also called as Hounsfield unit. So here what we calculate the value for the linear attenuation coefficient of each pixel. For each pixel, what is the linear attenuation coefficient will be calculated, and that is called as CT number. So this will give you the detail or the information of the picture. Going to the equation to calculate CT number. So CT number can be calculated by equation, which is HU is equal to mu T minus mu W by mu W into K. So it means mu T, one second. So CT number, we have an equation which is HU is equal to mu T minus mu W by mu W into K. So here mu T stands for the linear attenuation of the tissue, and mu W stands for the linear attenuation of water, and K is a scaling constant which is always 1000. So mu W is 0.19 centimeter raised to minus 1 at 73 kilo electron volt. So HU stands for CT number. So we have the equation which is mu T minus mu W by mu W into K. So if you know the linear attenuation of the tissue and this mu W and K we already know, we get the HU value. We'll have a small calculation. So here we have HU, the tissue have a linear attenuation coefficient. We are calculating the bond. So bond have a linear attenuation coefficient of 0.38. So we minus this 0.38 by 0.19 divided by 0.19 into 1000. So it will be 0.19 by 0.19 into 1000, which is 1000. 1 into 1000, which is 1000. So we get the CT number value of bond as 1000. So different part have different CT number. For bond we have 1000. Basically we have to know bond, water and air. Bond we have 1000, water we have 0, air we have minus 1000. So that is the main CT number. And others also you have to know. For muscle it is 50, white matter we have a CT number of 40, gray matter 30, blood 20, CSF 15, fat have minus 100. So these values have to be known. So basically bond 1000, water 0 and air minus 1000. So we have something called as window width. So window width is like the range of CT number. We have a specific, like here we can say our we have minus 1000 to plus 1000. So that range is called as what? RCT window width. So here if we take a specific window width, like from this part to this part, whatever CT number is within there will be the window width. And in the center, for example, if I am saying we are taking minus 1000 to plus 1000, so this is your window width. We have something called as window level or window center. So window level or window center is something where the center of this window width. So here minus, when we consider the window width as minus 1000 to plus 1000, which one is the center? 0, right? So 0 will be our window level. So like this we'll calculate. We have the entire range is considered as window width. If for example, if you are taking this as the window width, the center of that will be our window level. So that's all about the basic principle. Now going to the generation part. So generation, this EMI scanner was the first scanner which we have seen, it was a dedicated head scanner. We can do only a dead scanner, and the patient head will be in a rubber membrane, and we keep the head into water filled bath. So this water filled box will rotate 1 degree with the single detector assembly. So like this patient will be, this head will be having a rubber membrane which will be kept over the water filled bath, and this box will rotate 1 degree along with the single detector assembly. So here you can see head will be 17 centimeter wide. Here this is a rubber head bar bag, and it will be in a 17 centimeter wide water bath. This is your water bath, and there will be X-ray tube above, and there will be one detector which is sodium iodide detector below, and the X-ray tube anode will be stationary anode tube, and we have single highly collimated heavily filtered parallel beam. Like this parallel will be beam will be there. So there will be a reference detector before it reaches the patient to know the value. So going to the generation, we have basically 7 generations for first, second, third, fourth, fifth, sixth, seventh, like that. We have 7 generation. We'll discuss about each. So for first generation, we have only parallel beam. Like this parallel beam will be produced for the first generation CT scan, and it was used by Hounsfield. So the EMI scanner was based on this process. I mean this principle, first generation. So we have something called as translate rotate principle. Means this X-ray beam and single detector will move one, then it will rotate. So like this. It will move once, rotate. Again move, rotate. Move, rotate. Translating. It's move along the patient, it will rotate. Like that. Not the continuous rotation. So we have single X-ray tube and single detector, and we have linear. Since we have this translate rotate, we can call it as linear and rotate. And total motion is 180 times in 1 degree interval. So we have rectilinear pencil beam scanning. So it will take around 4.5 to 5.5 minutes to complete the scan. You can see here. Once it will move, rotate. First, it will translate a patient moving. Linear motion, rotation. Linear motion, rotation. Like that, it will be moving. So advantage, we have minimal scatter radiation, and disadvantage, it will take more time, and the patient motion is restriction. Like if the patient move, it will have a problem, and body scanning was not, entire body scanning is not possible. Then we have the second generation. In second generation, we have done this mainly to reduce the scan time. And here what we used is, we used, instead of pencil beam, we used a narrow fan shaped beam. So for that we had multiple detector. Here in the in the first generation, we had single detector. Here we have multiple detector. Maximum of 30 detector we have used in some machine, and this is also based on the translate rotate motion only, linear motion, then rotating like first generation. Only difference is that we had fan beam. Since we used multiple pencil beam, we get a fan beam, and we had multiple detector. So what happened after one translation, tube and detector will rotate with a large increment compared to the first generation. So it's a rectilinear multiple pencil beam scanning. So scan time is 20 seconds to 3.5 minutes. Advantage, we require only fewer linear movement because there is more detector and fan beam is produced. We require only fewer linear movement, and scan time is less. Going to the disadvantage, we have more scatter radiation, more noise is produced, and motion artifact is also there. Going to the third generation, I hope the first and second is clear for you people. Going to the third generation, this is based on the fan beam. So here the fan beam, what happened? They will rotate continuously. So the X-ray tube and the detector will be coupled, and they will be in an arc. The detector will be in an arch of 30 to 40 degree, and the X-ray tube and the detector will continuously rotate. So we have rotate system, and this tube complete circle motion will be there, and we can get the scan time within 4.9 seconds. Like this, we'll get continuous rotation in the third generation. So advantage, we get fast acquisition. So since there will be less respiratory motion artifact, high spatial resolution, and scan time is less. Disadvantage, we have ring artifact formed and little bit expensive. So now going to the fourth generation. Fourth generation, we have two types. One is rotating fan beam within a stationary ring of detector, and second one is nutating fan beam with the apex of the fan is located outside a nutating ring detector. So here rotating fan beam within a stationary ring of detector. So this is your detector. This line is detector. So what happened? There will be X-ray tube inside. So when it moves, what happened? Detector will get the signal. Whereas in the nutating fan beam, X-ray tube is like ring uh, outside the ring of detector. I'll show you the image. First one, which is rotating fan beam within a circular detector array. So here X-ray tube will be in the within a stationary detector array. This is your detector array. Inside that we will be having the X-ray tube. So beam geometry, we have a fan beam. So what happens when the X-ray beam goes? It will detect in this side, and when the X-ray beam reaches here, this part of the detector will get the signal. So as the tube move from point to point within a circle, single ray strike is detector. Some single ray will strike the detector, and then they produce a circular travel. Here scan time is short, and we get uh, a circular path of the X-ray tube. Here X-ray tube is rotating, whereas the detector is stationary. Going to the next one, which is rotating fan beam outside a nutating detector. So nutating means where it rotate on its own axis. So consider this is your axis. This detector will rotate on its own axis, and this X-ray tube also will rotate. So for example, if I say this X-ray tube will rotate outside the detector. Here we have the X-ray tube. So here we have the detector. This inside you will have the detector assembly. So here will be the patient. So when the detector is this here, the X-ray tube is here, this part of the detector will be exposed. Same like when the detector comes here, same like this part we will be having this side. So that part will be exposed. Like that will be the exposure, and scan time is 3.4 seconds. So advantage for this is higher efficiency, and it have high spatial resolution, and there we don't require any mechanical motion for the detector. So disadvantage, we don't require any detector coordination, and we have a little bit scatter artifact will be there, and if there is some detector element, if one or more detector element if not working, you will not get good image. Going to the fifth generation is also we have two types. One is electron beam CT, and another one is dynamic spatial reconstructor. So going to first, which is electron beam CT. So here we get higher resolution image of like heart and all with three artifact. Here we don't require any electron X-ray tube. What happen is here it's 10 times faster than the conventional CT. So what happened inside this is here you have an electron gun. So this electron gun will produce electron, which will be with the help of focusing coil. It will be focused. So here you have the electron beam, which will come and strike over the target ring. So the target ring is made up of tungsten. So when the electron gun produce electron and comes and hit electron beam comes and hit over the target ring, which is made up of tungsten, X-rays will be produced. So that X-ray will pass through the patient and detected by the detector ring. So here there will be a gun which produce electron beam, and there will be focusing coil, deflecting coil. Focusing coil focus all the electron beam. Deflecting coil will help to deflect it, and it will be deflected towards the target ring. So this target ring will be made up of tungsten. So that time what happened? X-ray will be produced. When electron hits over the tungsten, electron will be produced, which will be sent through the patient. Here the entire circle, one half will be target ring and one half will be detected. So we have 216 degree angulation in the detector. So there is no mechanical motion of the component. It will not move. And we have something called as DSR, which is dynamic spatial reconstructor. So we get 3D images of the volume of the patient. So what happened? There will be multiple X-ray tube in an arc of 160 degree, and we'll have a detector in the arc of 1600. So like this, we will be having multiple X-ray beam, and this will be in an arc of 1600, and there will be multiple video imaging system. So it will be very fast. Now there is no much explanation for this DSR, only this much. So we get in a one exposure, we get around 250 slice for this DSR, and the slice thickness is like 1 mm, like 60 frame per second you'll get. So then detector will send the image to the DAS. Going to the advantage of the fifth generation, it's fast, and fast acquisition is there, and we get high resolution image of the moving organs, and it's free of motion artifact, and where there is no mechanical motion, and you get image very reconstruction is fast. And disadvantage, it's little bit expensive and will require a larger space, and the SNR is less, signal to noise ratio is less for this fifth generation, and we have more radiation dose, and slice thickness is more here. So going to sixth generation is a dual source CT scanner. So here in the dual source CT scanner, it consists of two X-ray tube here, like two X-ray tube and two set of detector in a 90 degrees.
Each delivery like up to 1300 MAS at 70 kV. The output of both tubes can even be combined.
So this will improve the spatial and temporal resolution in cardiac CT. So dual energy CT is new application. So compared to the conventional or single energy CT, this have like here what we do in the single CT, we require the single energy CT, we use 70 to 140 in a standard of 120. In dual energy, we use two X-ray tubes which produce two energy level. One will be 80 and one will be 140 kVp. So we can one X-ray source will produce one energy level and other will produce another energy level. So we have two techniques in the dual energy CT. One is low kV switching and another one is high kV switching, fast kV switching. So here in the slow kV switching, what happened was here this technique is followed only for a dual energy CT which produce single source, like one X-ray tube only will be there which produce two energy. In that case, X-ray tube first will produce high kV, then there will be a small delay, then it will produce low kV, then the table will move, like that is low kV switching. Whereas in the fast rapid switching, what happened, high kV, low kV, both there won't be any delay and the table increment. You can see here blue color is low kV and black is high kV, like overlapping it will be. And another for this thing is in dual energy CT, instead of detector, we have using two detector, we have multi-layer detector. So it consists of two layer. So one layer will have front layer for the low energy data and the back layer to get high energy data. And this, as I said, dual source tube will be rotating on for like if when we require low energy, the 80 kVp X-ray tube will be working, and when we require high energy 140 kVp X-ray tube will be working. So it's application to find out the different types of renal calculi. Not only to find out the presence of renal calculi, we have different types like uric acid, cystine, like that. We have different calcification in the calculi. So to find out which calculi we can use this, and to find out the water-filled cyst without the use of contrast media. So advantage, we get fast 3D image in the sixth generation, and its cardiac imaging is possible in this. Disadvantage, it's little bit expensive and radiation dose is more. Going to the last generation, which is seventh generation, we use flat panel detector, and X-ray tube and detector will be coupled. Instead of normal detector, we use a flat panel detector here. We get cone-shaped X-ray beam. So the detector which we are using is cesium iodide scintillation coupled to TFT, thin film transistors, and we get better spatial resolution, and this is used for the CT scan of the breast. So advantage, we get fast 3D image and improve spatial resolution, and its disadvantage, it's a little bit expensive and contrast images are less. Okay, so going to summary, we learned this first generation, which is our EMI scanner. We used pencil beam. We have one detector and it's translate rotate. And second generation, we have narrow fan beam, multiple detector will be there, translate rotate. Third generation, we used wide fan beam, which will be continuous rotation. So rotate, rotate. Fourth generation, we used again wide fan beam where we had the stationary ring. So rotate stationary is used, and also rotate because two types is there in the fourth generation. And fifth generation we are using wide fan beam where there is stationary ring, so it's stationary. Sixth generation it's fan beam, it's third, fourth generation plus stable motion. Seventh generation it's con beam. So I'll just summarize. That was a little bit difficult, I think. So I'll just summarize. First generation, we were using translate. We were having single parallel beam and it's translate rotate motion. Second generation, we were using fan beam. It's translate rotate motion. In third generation, we had a multiple detector, which will be in angles and it will be completely rotating. In the fourth generation, we had two types. Uh, Rotating detector outside the rotating fan detector and rotating fan beam inside the X-ray beam. So its complete rotation motion is also there, and of sometimes detector one move also. Going to the fifth generation, we have two electron beam CT and dynamic spatial reconstructor. And sixth generation, we were using dual source spiral CT. And seventh generation, we had the flat panel detectors. That's all about basic principle. Stay back. We have one more topic to be taken, which is our instrumentation part. So I hope this basic principle and the generation part is clear for you people. We'll be continuing the class with the CT instrumentation. So what all instruments we are using inside the CT system, we have to discuss that also. So I hope you can see the screen is visible, I think. So we'll start with the CT instrumentation. So CT instrumentation, like what all instruments or what other technique, materials we are using inside the CT system. So there is mainly three major system inside used. One is the imaging system, second one is the computer, and third one is the display, recording and storage system. So in the imaging system where we perform the CT scan, computer system where this computer room is there, and then we have the display, recording and storage system which is located in the operator room. This is what imaging system where our CT scanner gantry is there, computer system where our computer system, and where we see the image, store it, and will send it to communication. So imaging system main purpose is to produce X-ray. They shape and filter the X-ray beam so that it passes through the body, and that we have the detector where it will convert the photons into digital information. So this imaging system have different components in the gantry itself, and the gantry and the patient table or couch all are referred as the scanner. So major components of the imaging system, we have X-ray tube and generator which produce X-ray, collimator so to define the slice thickness and restrict the X-ray beam. We have filter to filter out the radiation beam and protect from low energy and ensure uniformity in the detector. And we have the detector which will capture the photon and which will convert it into electrical signal. So this is our CT system. So we have gantry. So gantry is the mounted framework that surround the patient in a vertical plane. So this is your gantry. This part is your gantry. So this in the gantry there is slip ring, high voltage generator, X-ray tube, collimator, filters, detector, and data acquisition system. So going to the cooling system of the gantry, we have air temperature. Like when there is high temperature of this air, it will affect the components inside the gantry. Long before we were using air condition, which is placed ACs, which is placed inside the gantry. Nowadays we have circulating air from the scanner room throughout the gantry. Like we use large or low pressure blowers and filter, and there will be circular duct in the front of the gantry which will direct cool air so that the detector module and the gantry electronics will get much amount of air. And the maximum temperature which we are using is 23 degrees Celsius, and the humidity is around 60 degrees. So in the gantry, we have two important features. One is gantry aperture, second one is gantry tilting range. So this part is your gantry aperture. So most of the scanner will have around a diameter of 70 centimeter aperture. So this circular thing is your gantry aperture. So tilting range is this gantry will tilt. So this depends upon the system. There will be plus or minus 12 to plus or minus 30-degree tilt can be done. So which will have a 0.5-degree increment. And there will be in the gantry there will be set of laser beam also. Other than this, we have a gantry control panel will be there where we can define the tilt and the laser light and whether to put the couch inside, outside, zero couch position like neutral position, couch up and down, home button like when we press the home button, the couch will come out and down, and we have an emergency stop button, and we have exposure indicator, everything in the gantry control panel. Going to the patient table, it's a platform where the patient will be lying down for the examination. It should be strong and rigid, and they provide safety and comfort. And this table is kind of a floating table like this. This part will be floating. This will be a pedestal which will be still. This part will be floating front and back. So couch top is made up of carbon fiber composite. So they provide low absorption and vibration damping, and like it have two types of motion. One is longitudinal motion, and the other one is vertical motion. So longitudinal motion means inside out, vertical motion up and down. For the longitudinal motion, it will have a stroke, like it can go 1900 mm. Scan range, we can scan around 1620 mm. Speed, how it goes is 0.5 to 143 mm per second, and we get around plus or minus 25 accuracy. Whereas in the vertical motion, its scannable range is around 526 to 1040 mm, and speed is 2.5 to 50 mm per second. And this table, patient table, have a capacity to load around 240 kg. Other components of gantry, we have generator, X-ray tube, filters, collimator, detector, and detector electronics. So this is your internal view of the gantry. If you have been working in CT system, or you have during a like, academic study, you have seen a CT like any how when this it was opened, this will be familiar for you. Here we have X-ray tube, and these are the filter, collimator, reference detector. We have internal projector here, and we have X-ray tube, heat exchange like oil cooler, and we have high voltage generator, and we have direct drive gantry motor to rotate it, and we have rotation control unit, and we have data acquisition system. Here we have our detectors, and we have our slip ring here. This is your slip ring. Slip ring can be seen. And then detector temperature controller here is there. And we have the high voltage generator. We have our power unit and line noise filter. Like that, many things are there inside the gantry. So there is something called a slip ring technology where which allow you to continuously rotate. That's in third generation we learned continuous rotation of the X-ray tube and detector. This is made possible by the slip ring technology. So in the slip ring technology we have two design. One is disc shaped and one is cylinder shaped. So disc shape it will be like 2D, whereas cylinder it's a shape of 3D. So in the disc there will be concentric rings circling in one plane of rotation, and here in cylinder conductive rings will be there in the axis of rotation like this. This is your disc and this is your cylinder, like it's in a 2D way, this is in a 3D way. So in the slip ring we require brushes, and we require brush and sorry, this can brush. So brush, we have two brush design. One is wire brush, other one is composite brush. Wire brush means there will be one or more wire within. This is the brush block, and this is your this module. So this module there will be one or more wire arranged so that it will be rotating. Whereas here in the composite brush we use, instead of wire we use composite material like silver graphite alloy as the sliding contact. So this there will be different design to maintain contact between the brush and the ring. So slip ring technology based on the power supply we have divided into two. One is low voltage slip ring and the high voltage slip ring. In the low voltage slip ring from the AC main supply, it will directly send to the slip ring, and then the signal will send to the high voltage generator, X-ray tube, thus image reconstruction and image display. Whereas in the high voltage slip ring, after AC main, it will send to the high voltage generator where the voltage have been increased, and then will send to the slip ring, then to the X-ray tube, thus and so here difference is that high voltage slip ring, high voltage generator will be before the slip ring, whereas in the low voltage slip ring, high voltage generator will be after the slip ring. So advantage, we get continuous rotation of the X-ray tube, we get the volume data, and we get faster scan time, and the protocol which have continued acquisition and all can be used, and there will not be start stop like conventional scan. We have start stop process which will be not there, and there won't be cable wrap around the process. So next part is generator. So conventional CT generator, like olden times, we are using three-phase generator, which will be located near the gantry, which require a high tension long cable, and it have high heat load, and the X-ray tube life will be less, which have been replaced by the modern CT generation generator, which is small solid state generator, which have high frequency generator, which operate between 5 and 50 kilohertz, and the power rating will be around 30 to 60 kilovolt, and we can select the large exposure techniques. So we have medium frequency generator and high frequency generator, where the medium frequency convert in standard 60 hertz into 6500 hertz before it's sent to the transformer, whereas in the high frequency they convert low voltage low frequency current to high voltage high frequency current. So medium frequency generator we use for the normal radiography, whereas high frequency generator we use for the CT scan. Next, we have X-ray tube. We have in the first generation and the second generation and all, we were using fixed anode oil cooled X-ray tube. Uh, so afterwards, what happened? The rotating anode X-ray tube have been used. So anode disc is usually made of rhenium, tungsten, and molybdenum, and we have a small target angle, and the rotation speed will be 3,600 rotation per minute to 10,000 rotation per minute. So in the X-ray tube, we have normal three types. One is conventional all metal disc, one is brass graphite anode disc, and graphite anode disc. Here, what happened? The base body will be made up of titanium, zirconium, molybdenum, and then focal track layer. This is the focal track layer. This will be made up of 10% uranium, 90% tungsten, and they transfer heat quickly. Whereas in the brass graphite anode disc, in brass graphite anode disc, base body is made up of, this part is made up of graphite, and the focal track layer which is made up of tungsten and rhenium. Sorry, this is your focal. This black color, little darker. This is your tungsten rhenium. One second. And then we have graphite anode disc, where base body is graphite and the focal track layer will be tungsten rhenium, and they are lightweight and they have large heat storage capacity. So nowadays we have something called a Straton X-ray tube. So the main thing for the conventional normal X-ray tube is that heat dissipation is little difficult and slow cooling rate. So this have been replaced by the Straton X-ray tube. Uh, this have been like we have anode disc. So this is how your Straton X-ray tube will be there. So in the rotating anode X-ray tube, what is happening? Only anode will be rotate. But here in the Straton X-ray tube, anode and cathode, everything will be together like this. So this like a drum kind, there will be cathode which will be sent to the anode. So X-ray will be so, so entire thing will be rotating. So there will be oil for the cooling. Uh, Cathode assembly is deflecting to strike the anode. Like this, it will deflect, and the motor will be there, which will provide the rotation of the entire tube, which will be in the or immersed in the oil. So this is your conventional one. Yeah, this is your conventional one. This is your stratum. So in the conventional, what happened? Cooling oil is outside, so anode will heat up faster. Okay, whereas here it will be inside only. So cooling oil is inside only. So there is less heating of the anode. Heat will fastly exchange. Here, since here it is, there will be slow heat exchange. Then we have X-ray tube heat exchanger, where a cooling oil will be placed to cool this, and there will be refrigerating circuit which cools the cooling oil also, and there will be heat buffer to absorb the more heat load, and the walls will be there for that to dissipate the heat. And temperature control unit, we have two types. One is air cooled and water cooled. So in the air cooled, the heat is rejected. It will be sent to the ambient air through the fan with the help of fan, and there is no water quality and all. There is no requirement of external chiller. Whereas water cooler, heat will be rejected to water source, like there will be cooling tower plant, water system and all. Heat will be rejected to that water source, and there is no noise. In the noise is will be there by the fans, and it's cleaner, and there won't be any dust and dirt. So rotation control unit, so this helps to control the rotation. One second. The gantry rotation can be controlled by control unit. And then we have filters. So X-ray photon, which will be emitted by the X-ray tube, will be having a wide spectrum. So what happens? Filter will protect, absorb low energy and ensure only the high energy will be going. So we get equal filter. So olden times we were using normal filter. So that time what happened? Every patient's body equal energy will be reaching, but which have been little bit advanced, which is bow tie filter. So in the bow tie filter, what happened? The center part will be little compressed, whereas outside will be little thicker. So that time what happened? If the center part in our consider our abdominal area, center part will be what in the abdominal area? It will be thick compared to the side part. So what happens if we are using this kind of filter? Our side part and the center part will get same energy. So in the image, what happened? The center will be lighter, the periphery will be sharper. When we use this kind of bow tie filter, what happened? Center part will be little compressed, whereas side part will have more filtration. So that time what happened? Equal uniform X-ray beam will be coming. So that's about bow tie filter. So going to the collimator, collimator will give more image quality by reducing the radiation dose to the patient. So we have two types of collimator. One is pre-patient collimator, and another one is post-patient collimator. And pre-patient collimator is placed above the patient, and the post-patient collimator is post-patient is below the patient. So here like this, if this is the patient, this is your pre-patient collimator, this is your post-patient collimator. Pre-patient will be between the X-ray tube and the patient, post-patient will be between the patient and the detector. Function. So pre-patient collimator, we can define the size of the focal spot and reduce the penumbra effect, whereas post-patient we can control scatter radiation and improve the image quality. So we have next what is our detector. So detector, what happened? The radiation which is coming, the X-ray which is from the patient will be uh, radiation from the patient will be converting into the electrical signal. which will be then converted into the binary that thing. So we have four characteristics of detector. One is efficiency, under efficiency, one capture efficiency and absorption efficiency, and we have stability, response time, and the dynamic range. So this efficiency, like how efficient this detector is, and so ability to capture, absorb, and convert X-ray photon to electrical signal. So capture efficiency, ability to capture the radiation. So that is determined by two factors. One is the size of the detector, and second one is distance between the two detector. And absorption, number of photons detector can be absorbed. So that can be determined by the atomic number, physical density, size, and the thickness of the detector face. Stability, how steadiness the detector is, how it is responding. Whenever, like how strong it is, its stability. Response time, like when the detector detects some event, it had to be showing the image at the same time. There should not be any afterglow. That then, if there is any afterglow, there will be pile up, detector pile up. Next, we have dynamic range. So dynamic range is the like how much ratio of the largest signal to be measured to the precision of the smaller signal. How much like maximum largest signal and the smallest signal which can be discriminated. That is dynamic range. So most of the CT scanner have a dynamic range of about 1 million to 1. So the entire detection efficiency is calculated as capture efficiency into absorption efficiency into conversion efficiency. CT detector, this working is clear for you. Patient X-ray from the patient will be coming to the detector. So we have different types of detectors. One is scintillation detector, gas ionization detector, plug-in detector, dual slice, dual row detector, multi-slice, multi-row detector. Under multi-slice, multi-row detector, we have matrix, adaptive, and hybrid. So going to the scintillation detector, which we already discussed in the nuclear medicine classes. So what happens if X-ray photon from the patient will come hit over the scintillation material, which is sodium iodide crystal, which will convert the X-ray into light, which will be sent to the photomultiplier tube. And in the photomultiplier tube, we have photocathode, which will convert the light into electrons, and it will send to the dynode. Dynode, what they do, there is several dynodes which have which will multiply. So once if one signal goes, they will multiply two. So 2 into 2, like that, it will be multiplying at the end, and we have anode where we take out the signal. So it's like X-ray, scintillation crystal convert to light, then to PM tube, to the electrical signal, to the data acquisition system. So usually we use calcium fluoride and bismuth germanate as the scintillation detector. We have photodiode multiplied scintillation crystal detector. So instead of PMT, we use photodiode. So the light from the scintillation crystal will be sent to the photodiode, where they will convert it into electrons. Yeah. Next, we have gas ionization detector, which were used in the third generation. So this works on the principle of gas ionization. So there will be negatively charged plate here, and there will be gas, usually xenon gas. When the radiation hits, there will be ionization of the gas. So the positive charge will come to the negative charge plate, and the negative charge will go to the positive charge plate, which will be later amplified. X-ray to the gas chamber to the data acquisition system. This gas ionization also we have discussed in the nuclear medicine class. Now we have dual row detector. It was introduced by Elsint in the year of 1992. Here what happened, the detector, there will be two rows of the detector. Here you can see two row will be there for the detector. So there will be dynamic focal spot. There will be two, like we call it as twin beam technology. We get better resolution because we are using twin beam ray and detector sampling. Then we have multi-slice, multi-row detector. Like there will be multiple row. Like this, there will be multiple row. Here what happened? There will be one detector element which will be divided into different rows. One detector element will be made into cut. So this detector will influence the thickness of the slice. Advantage, it can have high volume coverage, high speed, and the data collection time will be less. Next is metric of mosaic array detector. Mosaic detector have uh, different types. There are elements which are uniform in size, or the section thickness can be 1.25 mm, 2.5 mm, 3.75 mm, 5, 7.5, or 10 mm. So this is one of the metrics or mosaic array. So here you can see equal interval. They will be equal interval. The detector will be of equal interval. That is matrix or mosaic. Going to the adaptive array detector, in this there will be variable size collimation, near focus collimation, and electron switching. I will show you the image. This will be your adaptive array detector. The center part, it will be 1 mm, then this 1.5 mm, 2.5. Like center it will be less, then towards the side the size of this detector element will be more. That is adaptive array. Then we have hybrid detector for different, like or anywhere it will be. So what basically center it will be 1 mm, side it will be 2 mm. That is hybrid detector. So we have recent advancement in the CT detector. One is gemstone detector, which was introduced by GE. Then we have nano panel prism detector, which was introduced by Philips. Stellar detector by Siemens. Quantum VI by Toshiba, and Pure Vision by Toshiba. These are the advancements. Next, we have data acquisition system. So this is a detector electronic system. So this is located between the detector and the computer. So the radiation from the detector, whatever have been detected by the detector, will send to the DAS, which is our data acquisition system. So they will encode this measurement into binary data, and this binary data will be sent to the computers. We have amplifier, which amplify the signal. We have log amplifier, which will convert it into logarithm value. Then we have ADC, which is analog to digital converter, which will convert this analog signal to digital data, and then digital data will be sent to the computer. We have CT computer system, which have large storage capacity and which can efficiently perform various kind of data. CT software, normal software is there, and we have reconstruction and image display. Nothing more to say, to display the image and to store the image. We have different storage like tape, disk, digital video tape is there, optical disk, tape, so many ways there. And for the communication, we have PACS, which is picture archiving and communication system, which is there for the almost all the hospital. And we also have DICOM, which is digital imaging and communication in medicine. So with this communication system, we can see the images or see the reports of the patient from anywhere of the hospital. Then CT control console have so many keyboards, touch panel, window control, image display, and all. So this is our floating keyboard. And this one is our floating keyboard. Then we have touch panel to set the parameter, window center to set the window width, image display control function and all. And we have some accessories for the CT system. So like to provide support for the patient. These are those. There is pediatric restraint kit for the restraining, immobilization, and we have elevator head holder for the head scan, and we have table extension. If the feet first case and all, we remove this head holder and we keep this table extension. We have coronal head holder for supine patient, then table pad, cushions, armrest, IV pole, and all. And we have pressure injector. So that's all about CT instrumentation. I hope it's clear for you people. So it's little bit easy part of CT principle and hardware. It's easy only. You have to know what are the equipments used. All those things have to be known. And normal principle, where the CT number, window width, window level, metrics, pixel, metrics, voxel, those things have to be known. And then the instrumentation, the what is a gantry, equipments inside the gantry, all those things, the slip ring, detector, gantry aperture, gantry tilting range, all those things have to be known. So that's all about today's class. We'll continue on the next. We'll see you on the next class. there is any doubt, like note it down the doubts, and for the live sessions we can discuss and clear out the doubts, and any further any doubts, and the questions for the same class we'll discuss on the live session. And I hope it's clear for you. Again saying, if there is any doubt you can note it down and ask me during the uh, during our online or the live session. That's all for today's class. See you on the next session. Thank you.